So in the last video we learned how to make polynomials that go through exactly through the points. So if you have 10 points you get a ninth order polynomial, always one less. Easiest way to think about that is if you have 2 points, then you would get a line of first order polynomial that goes through those. Now we're going to concentrate on getting a simpler, a lesser order polynomial. So we want to get a lower order polynomial that goes through the points. So say we want to approximate this. This is the polynomial that we made in the last video, and say I want to approximate it with this cubic. No, with this quadratic. It's an x squared. Basically, you need to find these three constants, a0, a1, and a2. And what we want is, we want to get, so there's a couple of ways to do this. One of the ways is we want this parabola to be as close to these points as possible. So we can do least squares minimization. When we put x in, when I put 1 in, I want 1 to come out. Well, what do I get when I put 1 in this polynomial? I get 8 in this parabola. I get a0 plus a1 plus a2. That's p of 1. So the difference between the 1 that I want and the output that I get for a particular a0, a1, a2 is, that's the difference, and I square it because we're doing least squares minimization. Likewise, if I put 2 in, I'm supposed to get 4 out. I want to get close. So 4 is the output I want. P2 is the polynomial with 2 plugged in, which would be a0 plus 2a1 plus 4a2. And this difference is I want to minimize the square of that difference, and so on. So I've got 5 points, and I want to minimize the sum of these squares. Now it's basically a calculus problem. Minimize this. So here's the parabola with 1 put in, the parabola with 2 put in, the parabola with 3 put in. So minimizing that is just going to be, this is a function of a0, a1, and a2. I want to differentiate, so this is let's call this m. I want to take I need the derivative of m with respect to a0, set that equal to 0. The derivative of m with respect to a1, set that equal to 0. I want to minimize that. So I've turned it into a minimization problem. And MATLAB will do those things. When you do ask it to do that, I didn't do it with MATLAB, I just actually took the derivatives. So make this a little bit smaller. So I want m, the derivative with respect to a0, that would equal to, so I have to differentiate all of these with respect to a0. That's going to give me one equation, so let's do that. So the 2 comes down, subtract 1 from the exponent. The derivative of the inside is, with respect to a0, is minus 1. Here the 2 comes down, subtract 1 from the exponent. The derivative with respect to a0 is minus 1. The 2 comes down, subtract 1 from the exponent. Chain rule puts another minus 1 out there. 2 comes down, subtract. I'm just doing chain rule like over and over again, so this is exciting. This is the derivative of this function with respect to a0. So I want to set that equal to 0. Then I'm going to have a derivative with respect to a1. Now that's going to put out a -2, so this becomes a 4. I lost my bracket here. This is going to put out a -3, so this becomes a -6. This one's going to put out a 4, so this becomes an 8. This one's going to put out, so it becomes a 10. And now that's the derivative with respect to A1. And I need one more equation. The derivative with respect to A2. That's going to match, that's going to put out a 4, that's going to be an 8. That's a 9, so that's an 18. 16, so that's a 32. And that's a 50. Anyway, 3 equations, 3 unknowns, solve. And that this is once I solve 3 equations, 3 unknowns, this should be the A0, the A1, and the A2 that I get. So this is a parabola that minimizes, that's the minimum y distance away from all of the proper points here. And there, so this, what looks like a straight line is not the straight line, that's the parabola. And this curved piece here, that's the 4th order. This is the upside down parabola, upside down 4th order here. So this piece is the upside down 4th order that and that exactly goes through the point 1, 1, 2, 4, 3, 9, 4, 16, 5, 17. And this is the piece of the parabola that minimizes the square of that distance. So what's the point of all this? You could use this as a technique to, instead of using this 4th order polynomial, you could use this 2nd order polynomial as an approximation to that function. So minimizing square distance is one idea. Another idea is you could use min-max norm, so you could just minimize the distance, the absolute value of the distance. That's why we up here when we do minimizing the sum of the square, the differences, we square the differences so that the distance, that p of 1 is away from 1 is always positive. Otherwise they'll cancel out. The other way to make it always positive is to just take the absolute values. This is just a straight command. So these are things that we could already do. Here's the new thing, Legendre polynomials. But its purpose is the same. The purpose of these polynomials is to create a smaller order polynomial that's close to your actual bigger polynomial. All right. The Legendre polynomials, the way I list them is maybe different. If you look this up on Wikipedia or Planet Math, they might use different polynomials. My Legendre polynomials always have a leading term of 1. So the first polynomial is just 1, the 0th order. So p sub 0, p naught is 1. P sub 1 is x, it has a leading term. P sub 2 means its leading term is x squared, 1x squared. P sub 3, 1x cubed. P sub 4, 1x to the 4th. Notice too that all of the even-powered ones only have even-powered x's. It's an x, 1x squared, 1/3 x to the 0. Here's the odd one, has x cubed and x to the 1. There's no even powers in here. This x to the 4th only will have 1x to the 4th, some number x squared plus some number x0. So we're going to find this. We're going to find the 4th order Legendre polynomial. So there are a set of polynomials. Now what's the deal with these sets of polynomials? The first thing we want to say is they're orthogonal to each other. It's like when vectors are perpendicular to each other. How do we check if two vectors are perpendicular to each other? We take the dot product and we get 0 if they're perpendicular to each other. Well, with functions, we need a dot product equivalent, and this is our definition of a dot product. It's called an inner product. So when we're taking the dot product or inner product of two functions, we multiply them, integrate from -1 to 1, and that gives us a number. If that number is 0, then the two functions f and g are orthogonal. So all of these polynomials, these Legendre polynomials, are mutually orthogonal. They're all perpendicular to each other. So P1 is perpendicular to P3, P2 is perpendicular to P3. They're all perpendicular to each other. So if I want to find what P4 is, I need to know what the A and the B are. So this is the condition that I need. I need that P4 dot product or inner product P, any of these other P's has to be equal to 0. So let's put in P sub 2 here. They're supposed to be orthogonal, so that has to be equal to 0. Well, okay, that means that if I'm dot producting them, inner product them, so P4 is this polynomial. We don't know what the A and the B are yet. And P2 is this polynomial. I don't know what the, well, I know what this one is. And when I do this integration, sub in the top, sub in the bottom, that's going to give me one equation with capital A and capital B in it. That'll make P2 perpendicular or orthogonal to P4. Oh, so let's get that out of the way right now. Since by definition here, when I take the inner product of two functions, I just multiply them and then integrate them, then f dot product g is the same thing as g dot product f, because I'm just integrating them. So let's expand this out, clean this up here. So now all I got to do is do this integration. It's a bunch of add one of the exponents, divide by what's up top. Will Scientific Workplace just do this for me? It will. So the B things must have canceled out. Oh yeah, notice that the, yeah, okay. When I did that integration, this gives me an equation for, oh, I forgot the minus sign. Did I? No, I did not. That, now I know what A is. I can solve this for A. So now I had two unknowns, A and B. By making P2 and P4 perpendicular, then I have one. I can make P P4 and P3 perpendicular to each other. So let's try that. I'm looking for another equation. So P and P3. So that means P3. Set that equal to 0. Do the same thing. Now when we expand this out, when we expand it out, oh wait, that's all odd powers. So let's think about this for a second. I'm going to be integrating all odd powers. When I integrate an odd power, they're all going to become even powers. So it'll all be some number even, x to an even power. If they're all x to an even power, when I plug 1 in, I get the same answer as when I plug -1 in. So this is going to be 0 no matter what numbers I pick for a and b. So that's, in fact, that's always going to be the case. If your two polynomials, if one's odd and one's even, when I multiply them together, I'm going to get all odd powers, and then when I integrate them, they're going to be all even, so I'm always going to end up getting 0. So that doesn't give me an equation with a and b in it. So P4 is already, just because it's even and P3 is odd, they're already orthogonal. P4 is also orthogonal to x, because if I multiply these two together, I'm going to get x to the 5 and x cubed and x. Integrate them all, it's going to be even, even, even. You get 0. So this doesn't help me. I need to take this with another, I need to integrate it with P0. That's the only other even powered one. So this should be just 1. When I expand this out or simplify this, I get one equation with a and b in it. And I already know what a is, so now I can figure out what b is. Then I'll know a and b, and I'll know the fourth order Legendre polynomial. Let's figure out that then. So this is my equation with a and b equals 0. I know that the a is supposed to be -6/7. So now I can solve this for b. So if we did everything right, this is what P4 should be. Now that might look different from the polynomial that you look up, because some people don't make their leading coefficients 1. Some people would write this as 3x squared minus 1, let's say. It's still going to be perpendicular to the other ones, but mine are not. They're not unit polynomials. Okay, what does that mean, a unit polynomial? Well, if I dot product a function, a polynomial against itself, and sure, you can do that, that equals to the magnitude of that polynomial squared. Just like if I dot product a vector against itself, I get the magnitude of that vector squared. Exact same idea. So here's me doing the same thing as we did up there. So now, if we want to make these unit polynomials, so these polynomials I have listed here are Legendre polynomials, but they're perpendicular. They're mutually orthogonal. They're all perpendicular to each other, but they're not 1 unit long. To make them 1 unit long, we could scale them, but instead I just figure out the magnitude of each one of these pieces. So here, to figure out the magnitude of a function, I just dot product against itself, integrate from, so that'll be 1, integrate 1, that's x, 1 minus a minus, that the polynomial 1 is 2 units, is root 2 units, so this is the squared of the size. How long is the x? When I integrate that, I get x cubed over 3. Plug in the 1 and the minus 1, you'll get 1/3 minus a minus 1/3. So the magnitude squared of x is 2/3, and so on. So this is me calculating the size of the first three polynomials. So now I have these. Okay, let's just collect ourselves here. We have polynomials, 4 of them. They're all perpendicular to each other. If I wanted the 5th one, then that would be, let's just say I wanted the 5th one. That would be x to the 5th plus some number x cubed plus some number x, right? All the odd ones from 5 down. I dot product against all of these and make sure that I got 0, figure out the constants that work for that. So we could make more polynomials if we need them. Okay, and we could figure out their size by dot product them against itself, and that should be the magnitude squared. All right, so what does that mean for us? So this is the polynomial that we're trying to approximate. So that's this polynomial. This f of x, then, that's our polynomial. That's our 4th order polynomial that goes through all these points. And I would like to project, I would like to see the dot product of this against all of the Legendre polynomials. So let's go. I want it dot product with P1, dot product with, P naught. So this is our function dot product with P naught. We get a number, right? When you take a dot product, you get a number. That's just a straight do that integration. This is our polynomial against P1, getting a number. This is our polynomial against P2, get a number. Now I'm stopping at P2 because I'm going to try and make a parabola. So I only need to go up to x squared. If I only need to go up to x squared, then I only need to go up to P2. P naught has constants, P1 has x's, P2 has x squared. So I'm only going to go up to x squared to get a parabola. And now I have f, our function, dot product against each one of these p's. Okay, that's these top pieces here. So that's this number. It's a sum. So I have the dot product of our function against P naught divided by P naught dot product P naught, which we already made up here, that's this 2, times P naught. Next piece is for 1. I need our function dot product against P1, that's this 112 divided by 9, divided by P1 dot product P1, that's this 2/3, times P1. Last piece, because we said we were only going to go up to x squared, take our polynomial dot product against P2, get a number, divided by P2 squared times P2. This is our Legendre polynomial. When I simplify it, there's the parabola I get. Okay, now this is supposed to be a parabola, a second order polynomial that approximates our function. That's what we're supposed to get. But you're not impressed. The red is the parabola we made with Legendre polynomials. The black is our original 4, and it doesn't look that great. But let me caution you that I'm going to zoom in. This is the big picture, right? This fourth order polynomial, that goes through the point 1, 1, 2, 4, 3, 9, etc. But if I zoom in to just look in between, I'm just going to look at our fourth order and our red new parabola that we made with Legendre polynomials, and I just look from -1 to 1, they're pretty good. It doesn't look good on the top picture. It looks okay. It looks really good. It doesn't look too bad on this bottom picture. We got to remember that when we made our Legendre polynomial, we were always integrating from -1 to 1. We're building this new polynomial, this new parabola. We're building this approximation in the interval from -1 to 1. So it's only supposed to be good in that interval. Now I know what you're thinking. You're thinking, well, what good is that, right? All my numbers are like outside of that interval. Though only the 0.11 is like even on the edge of that interval. Okay, you're right. So what we have to do then is we're going to have to, because Legendre works from -1 to 1, what we're going to need to do is take our polynomial. We're going to need to squish it. Right now our points go from 1, x equal 1 to x equals 5. So our sort of window goes from 1 to 5 where we have actual points. That's 4 units long. So I'm going to have to squish it down so it's only 2 units long, because the interval that Legendre works in from -1 to 1 is only 2 units long. So I'm going to need to take that parabola, squish it down by half, and move it over so that the middle is, so that it's in the interval. So I'm going to have to move it over. So here's going to be our plan. Take the fourth order function we have, squish it and move it into the -1 to 1. Then do the Legendre stuff and come up with a parabola. Then take that parabola and move it back to the 1 to 5 interval that we really want to work in. So take your function, move it into the kind of Legendre workshop from -1 to 1, do the Legendre thing there, and then take your answer and move it back. That's what we're going to do. So far what we did was great, but it was because we didn't move anything over. We're only approximating our function well from -1 to 1. All right. So let's think about that. We'll take a break.